So, welcome students. Today, so MA415 Algebra course. Okay, this is lecture number 2. Okay, so today we recall that we discuss about groups in our last talk. Recall. So, how to define groups? So we have a non-empty set G along with a map, so star. So let me write down star, and the star is a map from G cross G to G, and then it satisfies three properties. I hope you remember: associative property, existence of identity, and for every element, existence of inverse. Okay, these three properties. Okay, then we call this G is a group. Okay. So now onwards I will use this symbol. So this is what this is. Star is a take some say AB to map to A star B. So this A star B I will write down by simple AB, this notation. Okay, this is my notation. So now onwards I will not write down star, I will write down AB, and if it is addition then I will write down A plus B, otherwise for multiplication it is just AB. Okay, this is the notation. So recall we have discussed few examples in our last lectures. Maybe I can add some more examples. Okay, so some more examples. Okay, so maybe say 1. So we discuss about R plus. Okay, now if we consider real numbers which are only positive, R plus. So if you start with R with addition, then it forms a group that we discuss. But if you start with positive real number with the usual multiplication, then also it forms a group. Okay, it's a group. So it's also an example of a group. Okay, we check it. And another important example I should mention here. So suppose we have integer say n, any start with a natural number, a positive integer n, and what do? You take residue modulo n. What does that mean? So you have a set A, which are all those integers which are residue or remainder modulo n. What does that mean? So whenever you will divide any number by n, you check what are the remainder. So remainder can be 0 if n divides the number, it can be 1, it can be 2, and it can be up to n minus 1, right? Now in this set you are defining an operation. Say by this we have a, and you have a b, you choose another number b, and then you take addition, like something like that. So let me define by this n. So this is what? This is addition modulo n. What does that mean? So this means this is a plus b modulo n. Okay, I hope you knows what is a modulo operation, right? So you take a plus b and then you go divide by n and check what is the remainder. Okay, so that is this. So with respect to this operation, you check this is also a group. Okay, so this is obvious that this is a map from A cross A to A, right? Obvious. And this map satisfies associative property because associative property is coming in the associative property of the addition, and also inverse identity is a 0. So this element we generally write down by this bar notation: 0 bar, 1 bar, 2 bar, and then minus 1 bar. Okay, Clear? We can write by route done by these. Okay, so so you check that 0 bar is the identity, and similarly given any integer modulo n, the inverse minus n bar. Okay, so inverse minus n of bar is nothing but minus n whole bar. Okay, this is obvious. And it has a nice symbol. I will define later. Yeah, so this is actually defined by this symbol. I will tell you why this is this symbol. Okay, Z mod n z. Okay, yeah, when we will learn homomorphism theorems, then we will show you why this is called this symbol. Okay, so now so this is also an important example of groups. Okay, so again you can do something nicer from here. So you can only take say for example, let me use this symbol A star. Okay, so out of these many residual classes, you take only those which are co-prime to n. So it's kind of collection of co-prime. Co-prime means relatively prime. Okay, whose GCD is 1 with n. Collection of co-prime residues modulo n. Okay, and on this operation, on this set, you define the operation, say modulo n operation. Okay, like this, A star to A star to A star. Okay, and what is the operation? Operation is that you choose A bar and B bar, and you apply this operation, and you check that this is nothing but AB whole bar. So what is the meaning of AB whole bar? So this means that AB, so AB mod n. Okay, and it is closed under this, because if both A and B are co-prime, then product is also co-prime. So this is obvious. So this is an well-defined map, a function, whatever. Okay, so this is also important group which will appear many times in our lectures. Okay, so these are few examples. Obviously, now we are going to discuss much more important ideas, and this is for something called subgroups. Okay, so let me define what do you mean by a subgroup. Okay, subgroups. Okay, so I'm see the star I'm not writing, so I'm just only writing G. G is a group. Okay, so let G be a group, so it's non-empty and satisfying this property. Okay, a subset H, or rather a non-empty subset, I must say, a non-empty subset H is said to be a subgroup of G if H itself is a group under the same group operation. Whatever the group operation was there in the beginning, whatever star, dot, plus, whatever, same operation. Okay, under the same group operation. Then we call this is a subgroup. Okay, yeah, so subgroups is substructures, and you can obviously do many properties of subgroups with this. One of the most important. Okay, so let me give some example first. So example say one. So you remember that Z plus was a group, right? With this 50 addition, right? And so here, so this was my group G, and then I can choose my subgroup is collection of all the integers, say multiple. Okay, so maybe say first of all, say choose even integers, say 2, 4, 6, and dot. Similarly, -2, -4, and dot. Okay, so collection of even integers. Okay, so this is generally we call by the symbol 2z. Okay. Similarly, if we take another subgroup, say h dash, so multiple of this form n time z, is that z belongs to z, then also this is forms a subgroup which I get. Okay, and this subgroup is defined by these symbols nz. Okay, clear. And yeah, you can find out many subgroups or many groups. So given any group, you can easily find out some subgroups. Okay. Obviously, first the G itself. So the given any group G, so G itself is a, it's a subgroup of G, and also identity. So yeah, so I'm writing identity by the symbol 1. Okay, so something said connecting with identity only 1 is also itself a subgroup of G. Okay, and these two subgroups are called trivial subgroups. So they are called trivial subgroups. Okay, clear. So subgroups are nothing but the substructures, and in the substructures, what you can do, you can you find out the replica of group itself. So that means whatever the property is true for the group, you find out that every property is true for like those original properties are true for the subgroup also. Okay, so now one can ask that, okay, so are there any kind of okay, so let me tell here also. So in this case, generally we write down the subgroup by this notation H. This is the notation of subgroup. So this means that H is a subgroup of G. Subgroup Okay, so this is my notation. Okay, so now question is that do you have any easy way to find out, or rather some classifications or some properties which will tells that immediately tells that this is a subgroup? Okay, so the answer is yes. So we have such things. Okay, and then we will check that these are this subgroup. Okay, so let us just discuss some more properties. Okay, so um, theorem maybe you can say, or proposition or whatever. So let G be a group and H be a non-empty subset of G. Okay, so this is given. You have a group and H be non-empty subset of G, and then the following are equivalent. Okay, so the following are equivalent. We write down T, F, A, E in short. So that means the following are equivalent. So what are the following? That one, A is a subgroup of G, and number two, for all A and B belongs to H, if you choose any two element inside H, then A, B inverse also element of H. Okay, so whatever element you choose, A and B, you find out that the inverses are also element of that same group. So like product of this AB inverse is also element of the same element, same set. If you satisfy these two property, this property, then also it is a subgroup. Okay, so now how do you check this is a subgroup? This is why these two are equivalent. Okay, so it needs a proof. So let me give you quick proof. Okay, so proof. So let me first do it 1 and 2. Okay, so 1 implies 2. This is obvious, so this is trivial, right? Why I am saying this is trivial? Because if you know that H is a subgroup of G, then H itself is a group, and hence for any element A, B, you know that B inverse also element of H, so the product A, B inverse element. So this is trivial. So the interesting part is 2 implies 1. 2 implies 1. So what is given? So given that H is a non-empty subset of G, this is given to you non-empty. Okay, and for all AB belongs to H, AB inverse also element of H. Okay, this is given. So this is given. This is given. Okay. Now, as H is a non-empty subset of G, so let we choose A belongs to H, because non-empty set contains one element. Okay, and then this identity, which is I am writing by 1, this symbol A inverse also element of H, right, from this property, because A belongs to H, A belongs to H, then A into A inverse belongs to H, which is nothing but identity. So this means what? The identity identity is an element of H. Okay. And now for inverse, okay, so this is this one property. Now for now for so what you need to prove? You need to prove that for any element the inverse belongs to this. Okay, so now for any element you write down say B belongs to H, you need to find out B inverse belongs to H or not. But what is B inverse? So you know that 1 and B belongs to H, right? And this implies 1 into B inverse, which is B inverse is element of H, right, by the property. So for any element B inverse also element of H. Okay, clear? So what do you find out? You find out that non-empty subset H contains the identity, and for every element it has the inverse also, right? Do I need anything more to show H is a subgroup? Yes, so I need the most important property that the operation is closed. So what does that mean? So you remember, so there was a map from G cross G to G. So similarly, there should be a map from H cross H to H, right? So what does that mean? That means that the restriction operation from G is again a restriction operation from H to H to H. Okay, so what does that mean? That means that this operation must be closed under that group operation. That is what I need to prove. I need to prove that for, so that is uh, we need to show for all A B belongs to H, A into B also element of H. This is we need to show, right? Now how to show that? So you see already I know that, so let you chart, you choose any AB belongs to H, so let AB belongs to H, arbitrary element. Okay, arbitrary you choose, and then you know that this implies B inverse also belongs to H because 1 is element of H, and thus um, A B inverse belongs to H, which implies A B inverse whole inverse, which is nothing but AB. This is element of H. See, I just use the property that whenever two elements are there, then A that inverse also is element of it. Okay, and this completes the proof. So QED. This completes the proof. Okay, so if we have this property that is non-empty subset, satisfy the property that whenever two elements, element A and B element of H, then A B inverse also element of H, then you are done. Then this is a proof. Okay. In fact, if you know that H is a okay, so further, so note, so remark maybe. Okay, if H is a finite subgroup, this means finite. Kernel letter is finite. If H is finite, then then uh, then we have this. Then the following are equivalent. What are equivalent? That again, H is a subgroup of G and is closed under the operation for all AB belongs to A comma B belongs to H, A into B belongs to H. This is enough. You don't need A B inverse for finite subgroup, and that is also obvious. So obviously 1 implies 2 is trivial. Even 2 implies 1, you already get that closed under the operation. Only thing you need to find out that the inverse belongs to the set H. Okay. Now how do you show that the inverse belongs to the set? So given any element, say for any A belongs to H, you define the set, say SA by this symbol A square. A square means what? A into A, then A cube, A into A into A, and so on. Okay, and this is a subset of H. Okay, clear. This is subset of H, and you know that H is finite. So what does that mean? That means this terminates somewhere. So this infinite is apparently this SA look like infinite, but it is a subset of a finite set. So H is finite, right? H is finite. It is given to you, finite set. So it terminates. So what does that mean? That means so you must have, so there exists some integer n1 and n2 such that a power n1 equal to a power n2 and so on. So it will repeat. And what does that mean? So this means that a power n equal to identity where n equal to n1 minus n2. Okay, and this implies that a into a power n minus 1, which is identity. Again, you can write down thus a power n minus 1 into a, which is identity. So thus a power n minus 1 is nothing but the A inverse. Okay, so inverse exists for every such elements. Okay, and that is the proof actually. So this is the proof actually. Okay, so it's already closed, and you know that for any two elements if closed, then inverse exists, and the moment you know inverse exists, then identity also exists, because identity means A into A inverse, which is also element of each. Okay, so this is the proof. So for finite set, you don't need to check that A and B belongs to H implies A B inverse belongs to H. It is enough to check A into B element of H. Okay, clear? So these are some properties. Okay, so now let me define one more important idea. Okay, maybe I should say something here. Yeah, okay, so for the time being, we will learn one more idea and then come back to again these subgroup things, and this idea called homomorphisms. Homomorphism. Okay, so what does that mean? So you suppose um, you have two groups. Okay, so G1 and G2, and you want to find out some nice operation or map from G1 to G2. This preserve kind of the structures of G1 and G2. Okay, so how do you find out this kind of map? So so definition, I like how to define this. So uh, a map say phi from G1 to G2. Okay, so when I'm saying that, I'm not assuming that G1 and G2 have with respect to same operation. It can be G1 star 1 and G2 star 2. Operation can be different also. Okay, and G1 G2 can be different group, it can be same group also. So anything. So this is in general definition is said to be to be a group homomorphism or homomorphism of group, whatever you say, homomorphism if what happens if it preserves the structure. What does that mean? So if for a star 1 b, so you take two operation, two element in G1 and you take the operation and then apply the map, so the image will be it will be equal to phi of a, this is inside G2, so this is star 2 and phi of, okay. So okay, so how do you check it typically? So you have two groups, so G1 and G2, G1 and G2, and you have two elements, say A and B, and you do the star operation. It is AB or A star, whatever, and if this element has the image here, and this element has the image here, and if these two have, this is the image of these two. This is say phi A1, this is phi A and phi B, and this is say phi A whatever star to phi B, and then this is nothing but the image of this. Okay, so this map preserves the structures. So if you first apply the operation and then the apply, then it is same as first apply here and then do the operation. Okay, so these are this is very nice kind of map, and this is called group homomorphisms. Okay, and there are particular a nice homomorphism. So a bijective homomorphism is called, or rather is called an isomorphism. Okay, isomorphism. So what is that? So isomorphism means isomorphism this means this is homomorphism plus bijective map. Bijective means injective plus surjective, one non two. Okay, and then this is called okay. So let us give some example. Okay, yeah, so obviously given any group you have the identity map which is homomorphism. So this is trivial of, so for identity map from G to G is an isomorphism. Actually not only homomorphism, this is isomorphism. Okay, this is trivial example. So now let me start with some non-trivial example. So you remember that I showed that Z is a group with respect to addition, and then NZ is also subgroup with respect to addition. Okay, same addition, and here this is the modulo n obviously. Okay, and then I can define my phi. And what is my phi? So I'm taking any element, so any element here A, I'm sending it to A mod n. Okay, or rather I mean A bar, you can write down by this symbol also, A bar. Some people write down A n bar or whatever. No, I think this is not good, so it is better to write down just A bar. Okay, if you understand the meaning. Okay, A mod n. and you check this is an this homework. uh, Check that 5 is a homomorphism. Okay, this is obvious, you can check. And maybe another, so this is look like that these are operation are similar operation. Okay, so you can have question in your mind that are there homomorphism of groups which are kind of having two properly completely different operation. So let me give one such examples. Okay, so suppose we have this R with respect to plus operation and another subgroup, another group R plus with respect to the multiplication operation. Okay, and here I am defining my phi by this symbol. So I choose an element and it's kind of mapping to e power x. So e is the natural logarithm, the base of natural logarithm. Okay, the Euler number. So e Euler number. That you already know what is e. Okay, and you check that this is again a, so this is again homework. The phi is a homomorphism. Okay, these are you can easily check. Okay, so so this homomorphism have there are, you can find out lots of properties of homomorphisms. Okay, and also isomorphism. I will come and tell some of those things. So maybe let me define some more properties of groups and then this. Okay, clear. So one more important groups I should define it. It's called abelian group or commutative group. Abelian or commutative group. Okay. So this is named after the famous mathematician Henry Abel. Okay, so so a group G is said to be a an abelian group. Abelian group if for all A and B belongs to G, we have the product A and B is same as the product B and A. So if you're taking from one side and other side, it does not matter. Okay, so this is called abelian group, and you see examples. There are many examples already learned. Whatever we have learned, maximum abelian group Z plus R plus Q plus whatever the example, and there are counter example also. For example, you remember we learned matrix groups which are non-abelian. Okay, non-abelian. No. Sorry, matrix group with respect to multiplication. Oh, so let me define it. Okay, so you may not remember that. So let me define this non-abelian group like. Uh, so let me write down say GL2R. It's called general linear group 2 by 2 matrices. So what is this? This is collection of all 2 by 2 matrices such that your A, B, C, D are element of real numbers say R, and with this property, the determinant is non-zero. So what determinant? So AD minus BC. This is the determinant. This is non-zero. I check this collection forms a group, and with respect to multiplication, okay, so this forms a group with respect to matrix multiplication okay, but this is so this is an example of non-abelian group. This is an example of a non-abelian group. Oh my god. Non-abelian group, okay. Group as this matrix multiplication is not as not commutative, as matrix multiplication is not commutative. Okay, so now now if you have a group isomorphisms, so you can easily find out that, you can easily prove that um, so there are this kind of properties. And there are many properties I am just writing. So suppose so phi from say G1 to G2 is an isomorphism. Then there are many properties you can find out that they are true actually. Like for example, cardinality are same, and both are same property. Like if G1 is abelian, or this is if and only if, I should say. So it's not only if G1 is abelian, if and only if G2 is so. Okay, and then many such property satisfy. For example, okay, so I did not define what is an order of an element. They are also similar. There are many properties. They are same. Okay, so so group homomorphisms are those maps which preserve the structure of the group, and the special kind of homomorphism are called isomorphisms. Okay, which are bijective, and instead of bijective, if we have only injective, then it is called monomorphisms. Okay, so injective homomorphism are called monomorphisms, and surjective homomorphism are called epimorphisms. Okay, and if it is more both surjective and injective, is called isomorphism. So that means bijective. Okay, and there is one more thing I should teach you. Maybe I just define it and then you stop here. This is called cyclic group. So what is a cyclic group? So yeah, so cyclic group is a group which is actually generated by single element. So you remember diagonal group, we have two generators A and B. One is a reflection of order 2, another is rotation of order n. Okay, and we define this of group of symmetries of n regular n gon is exactly having 2n many elements. Okay. Similarly, you can talk about a group generated by a single element, and those are called um, cyclic groups. So a group G is called a cyclic group if G can be generated by a single element. So what does that mean? So that means that, okay, so let me write down mathematically. So that means that what? That means that is there exists one element, say x belongs to G, such that every element of G can be write as a power of this x. Okay. So in other words, you can write down G as kind of x power n. N is a integer. Okay. And this kind of group we write down by this symbol. Group generated by single element. This is the symbol. Generator symbol. Okay. And you have several example again. So cyclic groups, for example, Z itself, Z plus, right? So Z plus is generated by this one. One is the generator. Okay. Similarly, obviously, minus one also generates. Okay. And my question, homework. Now, if so, in that group, Z mod in Z with respect to this modulo n operator. Okay, so how many are rather first, what are the generators and then how many are those? So is a cyclic group or not? You find out first. Okay. Then number 2, what are the generators? Generators. I mean generators, I mean it can be, generator may be more than one also, right? You see in this example there are 2 generators. Okay. So if there are not, so this question you should think. Okay, and we can discuss in the today's this live session in the afternoon. Okay, we'll discuss it if you have further question. Okay, so thank you, and this ends today's talk. Bye.